Hey guys, tonight we're going to solve a quiet, everyday mystery that's written into your very own hands. Imagine you're at your desk, the morning light is just starting to filter into the room, and you're reaching for your first cup of coffee. Or maybe you're unwinding late at night, scrolling on your phone. Before you lies the simple object. Your brain sends a signal, your arm extends, and your fingers close around it. Without a single conscious thought, you've just made a decision, a choice that instantly connects you to a staggering 9 out of every 10 people on this planet. You chose a side. For the vast majority of us, it was the right hand that did the work, leaving the left to wait patiently for its turn. This simple reflex, this unconscious preference, is the final chapter in a story that began millions of years ago. A saga of survival written in scratched teeth, ancient bones, and the ghost-like outlines of hands on forgotten cave walls. So why this overwhelming bias for the right hand? What evolutionary storm pushed our ancestors down this one-sided path, while virtually no other animal on Earth followed? And what does it mean for the 10% who live in a world quite literally built for the opposite hand? Thanks to clues left in the fossil record and the latest scans of the human brain, tonight we will piece together this incredible puzzle. Frankly, you've probably made this choice 100 times already today and noticed it exactly 0 times. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. That small click sends a big signal to the algorithm. That long-form, serious, educational content still matters. And to me, it's an incredibly meaningful show of support. Thank you so much for helping keep this channel going strong. It always fascinates me to see where you're all tuning in from. Let me know in the comments where you are in the world and what time it is for you. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. That simple action, picking up the cup, is so automatic it feels preordained. But it is one of the most profound and uniquely human biases we possess. The global statistic hovers right around that 90% mark for right-handedness. This isn't a 50-50 coin toss, like the preference a cat might show for one paw over another when batting at a toy, which often evens out across the entire feline population. This is a species-wide, cross-cultural, deeply ingrained biological reality. It's a mainstream scientific fact that unites a stockbroker in New York, a farmer in the Mekong Delta, and an uncontacted tribesperson in the Amazon. The vast majority of us are living in a right-handed world. This skew is so powerful that it's woven into the very fabric of our languages and cultures. The word ambidextrous, which we use to mean equally skilled with both hands, literally translates from its Latin roots as right-handed on both sides. The root dexter means right, but it also means skillful or fortunate. The assumption is that the pinnacle of two-handed skill is simply to have 2 right hands. This begs the question, is this preference something we learn, a cultural habit passed down through imitation, or is it something far deeper, a blueprint handed to us by our distant ancestors? If it were purely cultural, you would expect to find at least a few societies somewhere on Earth, past or present, that favored the left hand. But we never have. Not one. The ratio remains stubbornly consistent. This points to an answer that isn't found in our schools or our customs, but in our evolution. To begin our search for that answer, we can't start in a modern genetics lab or with a brain scanner. We have to travel back in time to a place where the line between human and animal was still being drawn, to a dusty cave overlooking a river valley in modern-day Croatia. There, in the fossilized remains of our ancient cousins, the Neanderthals, we find our first tangible clue. We find it not in a tool, not in a weapon, but etched into their very teeth, a permanent record of a simple, everyday act, and a silent testament to which hand they chose to do the work. The air in the rock shelter is cool and heavy, with the scent of wood smoke and damp earth. You are crouched near the entrance, the afternoon light casting long shadows from the limestone overhang. Before you is a task that is as essential as it is tedious: processing a fresh animal hide. It's a messy, physically demanding job, but crucial for crafting the clothing, shelters, and bindings your family needs to survive the unpredictable Eurasian climate. The hide, slick and unwieldy, needs to be scraped clean of its remaining flesh and fat. To do this effectively, you need tension. You need both of your hands free, one to pull the skin taut, the other to wield the tool. Lacking a modern clamp or a helpful assistant at this moment, you resort to a method passed down through generations. You use your body as a vice. You grip a corner of the hide firmly between your front teeth, leaning back to create a tight, workable surface. Your jaw becomes a third hand. In your dominant hand, you hold your primary tool. It isn't a crude, shapeless rock. It's a piece of technology born from immense skill and knowledge. It is a flint scraper, part of the sophisticated toolkit known to archaeologists as the Mousterian tool industry. You or a member of your clan carefully selected this piece of stone, then, with precise, forceful strikes, napped away flakes to produce a sharp, durable working edge. Now, gripping the hide with your left hand and pulling it away from your body, you begin to scrape with your right. The motion is practiced, rhythmic, a steady drawing motion across the surface of the skin. Every now and then, your concentration wavers, or you hit a tough patch of sinew. The scraper slips. For a jarring split second, the sharpened flint edge skitters off the hide and grinds across the enamel of your teeth. There's no serious pain, just a faint, gritty sensation, and the quiet annoyance of a mistake. You reset your grip and continue, the minor incident forgotten. You forget it, but your teeth do not. That tiny accidental scratch is now permanently etched into your dental record. And over a lifetime of performing this task, hundreds of these microscopic striations accumulate, creating a clear and undeniable pattern. Fast forward 130,000 years. An anthropologist in a quiet lab is peering through a microscope at the fossilized incisors that were once yours. They see what you left behind. They see the scratches. And because physics is the same now as it was then, they can reconstruct your actions with startling precision. A scrape mark that runs diagonally from the upper left of the tooth to the lower right could only be made by a tool held in the right hand, moving from left to right across the anchored hide. A tool held in the left hand would create the opposite pattern, from upper right to lower left. And here is the revelatory finding. On your teeth, and the teeth of dozens of your Neanderthal brethren found at the Croatia site and across Europe, the scratches almost invariably run in one direction, upper left to lower right. You were right-handed. This isn't a theory. It is fossilized behavior. It is a ghost of a gesture, an echo of a preference, preserved in enamel. Of course, the academic world thrives on nuance, and so historians still argue whether this dental evidence is conclusive proof of population-level handedness or just a common technique for a specific task. Could it be that this one job was simply easier to perform this way, regardless of innate preference? It's a fair question, but the sheer consistency of the evidence is powerful. It suggests that the bias for the right hand wasn't just a quirk of our own species, Homo sapiens, but a trait we shared with our closest and now extinct evolutionary cousins. Our story of handedness, it turns out, has roots that go deeper than we once imagined. A shared trait with our Neanderthal cousins is one thing, a fascinating piece of the puzzle. But the story doesn't stop in that Croatian cave. To trace this preference back to its source, we have to journey deeper into the past and further south to the rugged Atapuerca mountains of northern Spain. Here, deep within a labyrinthine cave system, lies a chamber that is both a treasure trove and an enigma. Its name is the Cima de los Huesos, which translates starkly as the Pit of Bones. The name is brutally literal. At the bottom of a 43-foot vertical shaft lies the largest and oldest collection of early human fossils ever discovered. It is a tangled jumble of skeletons, the remains of at least 28 separate individuals who met their end in this deep, dark place 500,000 years ago. These were not Neanderthals, nor were they modern humans like you and me. They were an older, more enigmatic species, Homo heidelbergensis. These were stout, powerful people with large brow ridges and bigger faces than our own, but with large brains that were comparable in size to ours. As a species, they are a crucial character in our story, standing at a pivotal crossroads in human evolution. The current scientific consensus is that Homo heidelbergensis is the last common ancestor of both Neanderthals in Europe and our own species, Homo sapiens, which would later emerge in Africa. They are our shared grandparent, the trunk of the family tree from which our two lineages branched. And in that dark pit in Spain, amidst the tragic jumble of their bones, their teeth tell a familiar story. When scientists examined the incisors from the Cima de los Huesos, they found the exact same pattern of microscopic scratches seen on the much younger Neanderthal teeth. The same diagonal striations running from upper left to lower right, a clear and unambiguous signature of a right hand holding a tool and a left hand holding the work. This discovery was monumental. It took the timeline of human handedness and stretched it back into a truly immense expanse of time. At 500,000 years old, this evidence more than triples the age of the trait from what we saw in the Neanderthals. This wasn't a recent development or a regional quirk. This was a foundational characteristic of the human lineage, a preference that was already firmly in place long before our own species even existed. The bias for the right hand is an ancient family tradition. The site itself adds another layer of profound mystery. How did 28 individuals end up at the bottom of a vertical shaft? Archaeologists still fiercely debate the meaning of this assemblage. Was it a catastrophic accident? A whole group falling to their doom? Unlikely. Was it a place where bodies were unceremoniously discarded? Perhaps. But there is a third, more tantalizing possibility, supported by a single, extraordinary artifact found among the bones. A single, beautifully crafted hand axe made of reddish quartzite, a stone type not found anywhere else in the cave. Nicknamed Excalibur, this tool seems to have been intentionally thrown in with the bodies. This has led some researchers to suggest that the Cima de los Huesos is the site of the world's first known funeral rite, a place of intentional burial, a 500,000-year-old testament to symbolic thought and respect for the dead. Whatever the truth, the evidence is clear. The individuals mourned or discarded in this pit lived lives of dexterity and skill, and like us, they overwhelmingly performed those skilled tasks with their right hand. 500,000 years is a chasm of time that is difficult for the human mind to truly comprehend. To find a behavioral trait that remains consistent across such a span is remarkable. But the trail does not go cold in that Spanish pit of bones. To find the next clue, we must leave Europe behind and travel to the place where the human story itself began. We journey to the Great Rift Valley of East Africa, to a sun-baked canyon that has yielded some of the most important fossils in the history of science. This is Olduvai Gorge in Tanzania, often called the cradle of humanity. Here, the relentless process of erosion has sliced through the earth like a knife, exposing layer upon layer of geological time, each stratum a page in the planet's history book. And in these layers, legendary paleoanthropologists like the Leakey family unearthed the remains of our earliest ancestors, hominins who took the first crucial steps toward becoming human. Among these ancient inhabitants was a species known as Homo habilis, the handyman. They lived here around 1.8 million years ago, and they earned their nickname for a very important reason. They are one of the very first species in our lineage consistently associated with making and using stone tools. Theirs was a simple but revolutionary technology, the Oldowan industry, which consisted of breaking rocks to create sharp-edged cores and flakes. These were not the elegant, symmetrical hand axes of later species. They were crude, opportunistic, but utterly transformative. For the first time, our ancestors had a tool that could slice through thick hides, butcher a carcass for its calorie-rich meat, or break open a bone for its precious marrow. This was the dawn of technology, the invention that would set our genus, Homo, on its world-altering trajectory. And it is here, among the remains of the very first handy men, that we find our oldest clue yet. Scientists examining the teeth of a particular Homo habilis specimen, a fossil known prosaically as OH65, found something astonishing. There, on the 1.8 million-year-old enamel, were the familiar diagonal scratches. The same pattern, the same signature of a right-handed tool user that we saw in the Neanderthals of Croatia and the Homo heidelbergensis of Spain. The implication of this finding is profound. It suggests that our bias for the right hand isn't just an ancient trait. It may be as old as our identity as toolmakers. The moment our ancestors began to fundamentally alter the world around them by creating technology. They may have already been doing it with a preferred hand. Now we must proceed with caution. The evidence from this deep in the past is incredibly scarce, and this entire conclusion rests on the teeth of a single individual. Archaeologists still debate whether a single specimen can truly represent an entire species, or if this individual was simply an outlier, a right-hander in a population that might have been evenly split. Furthermore, paleoanthropologists still argue whether Homo habilis was a direct human ancestor or a side branch on the great hominin family tree. If they were a cousin and not a direct grandparent, it would mean that a strong preference for the right hand evolved at least twice in our broader family, once in their lineage and once in our own. But whether they are our direct ancestor or not, the clue from OH65 is a powerful hint that the story of our handedness is inextricably woven into the story of our ingenuity. The two traits may have been born together, a feedback loop, where the need for better tools drove the specialization of a single dominant hand. The story told by these ancient teeth is compelling. A single action, repeated over a lifetime, leaves a permanent mark that we can read millions of years later. But it's still the story of one specific task, processing a hide or cutting food held in the mouth. To build a stronger case, we need to find evidence of a more general, lifelong preference, a bias that shaped the entire body. We need to move from the accidental scratches on the teeth to the very architecture of the skeleton itself. And to do that, we rely on a fundamental principle of biology known as Wolff's law. This isn't some arcane theoretical concept. It's happening in your own body right now. The law, developed by a 19th century German surgeon, states that bone is not a static, dead scaffold. It is living, dynamic tissue that actively remodels itself in response to the loads and stresses placed upon it. Simply put, the more you use a bone, the stronger, thicker, and denser it becomes to meet the demand. If you want to see a dramatic, modern example of Wolff's law in action, you only need to look at a professional tennis player. From a young age, they spend thousands of hours performing a violently asymmetrical act, swinging a racket with one arm. Their dominant arm experiences immense torsional and compressive forces with every serve and forehand. Their non-dominant arm, while still strong and athletic, is essentially just along for the ride. The result is a startling difference, not just in muscle mass, but in the bones underneath. X-rays and bone density scans reveal that the cortical bone, the hard outer layer of their playing arm, can be up to 20% thicker and contain 40% more mineral content than the bone in their other arm. Their skeleton has literally rebuilt itself to withstand the demands of their life's work. Paleoanthropologists can apply this exact same principle to the fossil record. When they are fortunate enough to unearth both the left and right arm bones from a single ancient individual, they can perform detailed measurements, comparing the length, thickness, and markings where muscles once attached. And when they do this with Neanderthal skeletons, the results are crystal clear. Time and again, the bones of the right arm are significantly more robust than those of the left. The humerus, the large bone of the upper arm, often shows the most pronounced difference, mirroring the asymmetry we see in modern tennis players. This provides a powerful, independent line of evidence that corroborates the story told by the tooth scratches. The Neanderthals didn't just use their right hand for one specific task. They seem to have favored it for most strenuous, daily activities, shaping their very skeletons in the process. Of course, finding such complete specimens is the paleoanthropologist's dream, and a profound rarity. The journey from a living being to a fossilized skeleton is a brutal and chaotic one. After death, a body is often scavenged, trampled, and scattered. The bones that survive might be moved by water, buried under sediment, and subjected to immense geological pressures for millennia. It is a miracle that we find any fossils at all, let alone a matched pair of limbs from an individual who lived tens of thousands of years ago. This is why the tooth evidence remains so vital. It's a more common and reliable marker. But when the skeletal evidence does appear, it speaks volumes. Scientists still debate the exact cause of the extreme asymmetry in Neanderthal arms. Was it primarily the result of hunting techniques, like repeatedly thrusting heavy spear-tipped pikes into large game up close? Or was it the long daily grind of scraping hides, butchering carcasses, and working with wood and stone? In all likelihood, it was a combination of all these things, the sum total of a hard-lived, right-handed life, written directly into the bone. The evidence from teeth and bones is tangible, physical. It's the direct result of biomechanical stress and repeated action. But our ancestors left behind more than just their bodies. They left us echoes of their minds, their beliefs, and their sense of self. To find this next clue, we leave the open-air sights of Africa and the rock shelters of Croatia and descend into the deep, silent underworld of Paleolithic Europe. We enter the painted caves. Imagine yourself stepping out of the sunlight and into the absolute black of a cavern like Lascaux or Chauvet. The air grows still and cold, smelling of limestone and mineral earth. Your light, whether a primitive torch or a modern headlamp, casts dancing shadows on the undulating walls. And as your eyes adjust, they appear, vast, magnificent beasts galloping across the rock. Bison, horses, mammoths, and lions, rendered with a grace and confidence that is breathtaking. You are standing in a sacred gallery, a masterpiece of art created by people who lived more than 30,000 years ago. Among these stunning depictions of the animal world, you find something far more personal, more intimate, a human touch reaching out across the millennia. They are hand stencils, hundreds of them, clustered in groups or standing alone, like ghostly signatures on the cold stone. These are not drawings of hands. They are the direct incisors of them, a negative image surrounded by a halo of red or black pigment. They are one of the most immediate and haunting forms of art our ancestors left behind. A simple, powerful declaration. I was here. My hand, this hand, touched this rock. For decades, they were admired as a poignant connection to the past. But in recent years, scientists have realized they are also a massive, untapped dataset for understanding the people who made them. The technique for creating these stencils was simple but ingenious. The artist would place one hand flat against the cave wall. Then, they would take a mouthful of liquid pigment, finely ground red ochre or charcoal mixed with water or saliva as a binder, and spray it over their hand, likely by blowing it through a hollow bone or reed. It was a prehistoric airbrush. The result was a perfect outline. And this simple process contains a critical clue. To perform this action, you need two hands. One to place against the wall, and one to hold and direct the spray tube. The spraying is the skilled part of the operation, requiring dexterity and control. It is the action you would naturally assign to your dominant hand. Therefore, the hand you place against the wall would be your non-dominant one. With this simple, elegant piece of logic, archaeologists began to meticulously document and analyze the hand stencils in the caves of France and Spain. The results were staggering. Across thousands of examples, from dozens of sites, a clear and consistent pattern emerged. The vast majority of the stenciled hands are left hands. Study after study confirms the ratio, which hovers around 90% left hands to just 10% right hands. The implication is undeniable. The artists, the people who decorated these sacred silent places, were overwhelmingly right-handed. The 90-10 split that defines our world today was already present among the hunter-gatherer populations of Ice Age Europe. Archaeologists still debate the meaning and purpose of these hand stencils. Were they a shamanistic attempt to pass through the rock into a spirit world? Were they a form of sign language, with different hand shapes conveying different meanings? Some stencils even appear to be missing fingers, leading to grim theories of ritual sacrifice or a symbolic code. But whatever their ultimate purpose, their physical creation leaves us with one of the most beautiful and widespread pieces of evidence for the antiquity of human right-handedness. For a while now, we have been detectives on a cold case, gathering clues from the distant past. We have seen the evidence etched in the teeth of Neanderthals, measured in the bones of their ancestors, and spray-painted on the walls of Ice Age caves. All these clues point to one inescapable conclusion. Our profound bias for the right hand is not a modern quirk, but an ancient trait, with roots stretching back nearly 2 million years. But collecting clues only answers the what and the when. It doesn't answer the why. To do that, we must shift our investigation from the external world of fossils and artifacts to the internal world of the human body. We must go to the command center, the source of all action and preference, the 3-pound universe of tissue nestled inside your skull. The answer to why you favor one hand over the other lies in the elegant and mysterious architecture of your brain. Your brain, at first glance, appears symmetrical. It has two distinct halves, the left and right hemispheres, looking like the two halves of a walnut. But that visual symmetry is a deep illusion. Functionally, the two hemispheres are not created equal. This principle is known as brain lateralization, and it simply means that different mental tasks and functions are specialized to one hemisphere or the other. This specialization is the key to our entire mystery, and the most fundamental rule of this specialized system is the crossover. The left hemisphere of your brain is the puppet master for the right side of your body, and the right hemisphere controls the left side. This is called contralateral control, a basic wiring principle that runs through the nervous system. The signals that just told your right hand to move your mouse or scroll on your screen originated in the left half of your brain. Now, this division of labor in the brain is not a uniquely human invention. It's a mainstream scientific fact that some form of lateralization is found in almost all vertebrates. Birds, for example, often use one eye, and thus one hemisphere, to scan for predators in the sky above, while using the other eye to search for seeds on the ground below. This allows for a kind of parallel processing, a way to do two things at once, which provides a clear survival advantage. Even fish and toads show lateralized behaviors. However, what is unique to humans is the sheer degree of this specialization. Our brain is more functionally lopsided than any other primate's. While a chimpanzee's brain has some minor functional differences between its hemispheres, the human brain has taken this concept to an extreme, creating highly specialized modules for complex tasks. Neuroscientists still debate what specific evolutionary pressure drove human brain lateralization to become so much more pronounced than in our closest primate relatives, but the leading theories point to the increasing demands of tool use and language. Think of your brain not as a single, all-powerful CEO, but as a partnership between two brilliant but very different department heads. They are in constant communication via a massive bundle of nerve fibers called the corpus callosum, ensuring the whole operation runs smoothly. But each head has its own distinct portfolio, its own set of skills and responsibilities. And over the course of our evolution, the left hemisphere, for reasons we are about to explore, began to accumulate a very specific set of job titles. It became the specialist for the kinds of tasks that would ultimately define us as a species, and in doing so, it turned the right hand it controlled into the primary tool for interacting with the world. So we've established that our brain is a house divided, with each hemisphere managing its own set of responsibilities. To understand our right-hand preference, we need to open the portfolio of the left hemisphere and examine its specific job description. Now, you've likely encountered the pop psychology version of this. The left brain is the logical, analytical math whiz, while the right brain is the creative, emotional, artistic dreamer. This is a massive oversimplification. While there's a grain of truth to it, the reality is far more nuanced and interesting. Both hemispheres are involved in almost everything we do. The real difference lies in how they process information. The left hemisphere's true specialty, the common thread running through all its major functions, is processing things in a sequence. It is the master of order, of tasks that unfold step by step, one after another, where the order itself is critical to the final meaning. Nowhere is this more apparent than in its most famous responsibility: language. Nestled in the left hemisphere of over 95% of right-handers are two critical hubs of communication, two small patches of neural real estate that allow for the miracle of speech. The first is Broca's area, located in the frontal lobe. Think of it as the brain's sentence construction foreman. It takes the abstract, jumbled cloud of a thought you want to express and, through a breathtakingly complex process, organizes it into a grammatically correct sentence. It sequences the words, applies the rules of syntax, and coordinates the intricate muscle movements of your lips, tongue, and larynx to actually produce the sounds. Without Broca's area, you might know what you want to say, but the words would come out as a disordered, halting mess, a condition known as Broca's aphasia. Nearby, in the temporal lobe, is its partner, Wernicke's area. If Broca's is the speaker, Wernicke's is the interpreter. Its job is to comprehend the meaning of the sequences of words that we hear or read. It's what allows you to understand that the sentence, "The dog chased the cat," describes a very different event from "The cat chased the dog." The words are the same, but the sequence changes everything. Wernicke's area decodes that sequence to extract the meaning. These two regions, working in perfect concert, form the neurological foundation of human language. Here is where our story takes a crucial turn. What else requires the precise processing of a sequence of actions where the order is paramount? The creation of a complex tool. You cannot just randomly smash two rocks together and hope to create a functional Acheulean hand axe. It is a process, a reductional technology that requires a plan and a strict order of operations. You must first select the right core stone. Then, you must strike it at a specific angle with a hammerstone to remove a large primary flake. Then, you must turn the core and strike it again in another specific spot to shape it further. Each step builds upon the last. It is, in a very real sense, a physical grammar. This realization has led to one of the most exciting ideas in evolutionary science. Neuroscientists are still exploring the co-evolution hypothesis. Did the neurological architecture for tool use provide the foundation for language? Or was it the other way around? Did the step-by-step thinking required to make tools for millions of years essentially pre-wire our left hemisphere for the sequential syntax of language? Or did the growing need to communicate complex ideas, like how to teach someone else to make a better tool, drive the evolution of both language and the manual dexterity that controls it? Whichever came first, the link is undeniable. The part of the brain that handles our unique ability to talk is the very same part that handles our unique ability to create complex technology. It is the brain's master of sequence, and it lives in the left hemisphere. We've identified the left hemisphere as the brain's master of sequence, the conductor for both the intricate grammar of language and the step-by-step logic of tool making. Now, we're going to zoom in further, moving our magnifying glass over one specific neighborhood within this hemisphere, a tiny patch of cortex that appears to be the very nexus where our story converges. This region is known as Brodmann Area 44, or simply BA44. The name comes from a German neurologist, Corbinian Brodmann, who in the early 1900s painstakingly mapped the human cerebral cortex. He didn't map it based on function, which was largely unknown at the time, but on its cellular structure, its cytoarchitecture. He noticed that different parts of the brain had different arrangements and types of cells, and he divided the cortex into 52 distinct regions, like drawing counties on a map. It turns out this cellular map corresponds remarkably well with functional differences we've discovered over the last century, and BA44, a key part of the larger Broca's area we've already discussed, is a crucial county in our investigation. To understand why, I want you to imagine yourself inside the humming, claustrophobic tube of an fMRI machine. It's a device that doesn't see your thoughts, but it can see which parts of your brain are working hardest by tracking the flow of oxygenated blood. The researchers give you a simple instruction. They want you to imagine, as vividly as possible, that you are an early human making a stone tool. You don't move a muscle, but in your mind's eye you go through the entire process. You picture the smooth, heavy feel of the flint core in one hand and the hammerstone in the other. You mentally rotate the core, searching for the perfect striking platform. You simulate the precise, sharp blow needed to shear off a flake, visualizing its trajectory. As you run through this ancient mental choreography, on the screen in the control room, a specific spot in your brain begins to glow with activity. That spot, lighting up in response to the imagined sequential act of tool creation, is BA44, deep within your left hemisphere. This scientific evidence is our smoking gun. It demonstrates that BA44 is not just for language. It is the brain's primary hub for planning and executing complex, goal-oriented hand movements. It's where the abstract idea of a tool is translated into a concrete series of motor commands. And here is the simple, powerful connection that ties our whole story together. This specialized nexus for tool making resides in the left hemisphere, and the left hemisphere, as we know, pulls the strings for the right hand. The right hand, therefore, became the privileged and practiced appendage of this highly specialized neural machinery. This wasn't an overnight development. The mainstream consensus is that this system was forged under immense evolutionary pressure over millions of years. The journey from the simple Oldowan choppers of Homo habilis to the beautifully symmetric Acheulean hand axes of Homo erectus and heidelbergensis was a slow and demanding technological arms race. Each increase in tool complexity required a corresponding increase in cognitive horsepower. Individuals with a slightly more efficient or well-organized BA44 would have been better tool makers. Better tool makers would have been better hunters and providers, leading to greater survival and reproductive success. This created a relentless feedback loop, where sophisticated tools drove the evolution of a more sophisticated brain, which in turn conceived of even more sophisticated tools. Neuroarchaeologists still debate exactly when in our lineage EA44 took on this dual role for both language and tool making. Did it begin with the very first tools, or was it the invention of more complex multi-step technologies like the hand axe that truly solidified its function? Whatever the precise timing, this small region of the brain stands as a monument to the intertwined evolution of our hands, our minds, and our uniquely human preference for the right side. We've spent the last few chapters in the busy, industrious counties of the left hemisphere, marveling at its role as the master of language and the architect of tools. In this narrative, it's easy to cast the right hemisphere as the silent partner, the non-dominant side that was simply left behind in the great evolutionary race for specialization. But this would be a profound misunderstanding of how the brain works. The story of human success isn't about one hemisphere triumphing over the other. It's the story of an increasingly effective partnership, a masterful division of labor. So, while the left brain was busy sequencing words and planning tool-making gestures, What vital portfolio of skills was the right hemisphere perfecting? It was mastering the entire context in which those words and tools would be used. If the left hemisphere is a specialist in sequences and details, the right hemisphere is a brilliant generalist, a master of the big picture. Its primary domain is the world of the visual and the spatial. It's the part of your brain that allows you to effortlessly navigate your surroundings, to build a mental map of your house or your city. When you mentally rotate an object to imagine what it looks like from the other side, that's your right hemisphere at work. For our ancestors, this was an absolutely critical survival skill. The ability to navigate a vast and complex landscape, to remember the location of a water source or a good patch of fruit trees, and to find your way back to camp. These are the tasks of the right hemisphere. It is our internal GPS, our cartographer, our architect. Furthermore, the right hemisphere is a social genius. It holds one of the most important skills for a highly social primate like us, the ability to recognize faces. Your left brain might process the individual features, eyes, nose, mouth, but it's your right brain that synthesizes those details in a fraction of a second into a holistic, instantly recognizable identity. Evolutionary psychologists still debate whether our advanced facial recognition skills evolved primarily for identifying friend from foe within complex social groups, or for identifying and tracking individual animals during a hunt. Whatever its origin, this ability is foundational to our social lives. It also excels at reading the subtle, non-verbal cues that animate our interactions. It interprets body language and, crucially, the emotional tone of voice, a concept known as prosody. It's your right hemisphere that allows you to distinguish between a sincere "I'm fine" and a sarcastic one. The analogy of a film production is useful here. If the left hemisphere is the scriptwriter Tarn, meticulously arranging the words and the grammar to create a coherent story, the right hemisphere is the director. The director takes that script and imbues it with emotional weight, paying attention to the lighting, to context, the set design, spatial environment, and the actor's tone and subtext. One without the other is incomplete. You can have a perfect script that, without good direction, falls flat. This partnership is happening constantly. The profound importance of the right hemisphere's spatial duties is starkly illustrated by a strange and disturbing neurological condition called hemispatial neglect. Sometimes, after a stroke or injury to the right hemisphere, a patient loses not their sight, but the entire concept of the left side of the universe. They might only eat the food from the right side of their plate, shave only the right side of their face, or draw a clock with all 12 numbers crammed onto the right half. They are not blind to the left side. Their brain has simply deleted it from reality. This shows just how fundamental the right hemisphere is to constructing our basic model of the world. So, when our right-handed ancestor picked up a tool, the left brain planned the intricate sequence of hand movements. But it was the right brain that calculated the tool's position in space, its relationship to the material being worked on, and the overall context of the action. It was, and still is, a perfect partnership. We have seen how the brain's elegant division of labor provides a powerful neurological explanation for our right-hand preference. This lopsided structure, forged over millions of years of evolution, is the ultimate cause. But this raises a new, more personal question. When does this grand evolutionary blueprint actually manifest in an individual's life? When do you become right-handed? Is it a preference you are born with, or one that you learn? For centuries, the prevailing wisdom leaned toward nurture. It seemed obvious. A child is born into a world overwhelmingly designed for and populated by right-handers. They see their parents, their siblings, and their teachers all using their right hand for writing, eating, and throwing. The child, a natural mimic, simply learns to do the same. It's a clean, simple, and intuitive explanation. It also happens to be largely incorrect. To find the true origin of your own personal preference, we have to travel back to a time before you ever saw a parent hold a fork, before you ever held a crayon, before you even took your first breath. We have to go back to the dark, warm, aquatic world of the womb. For most of history, this early stage of our existence was a complete mystery. But with the advent of ultrasound technology in the latter half of the 20th century, we suddenly gained a safe, non-invasive window into this hidden world. Scientists could now observe the secret life of a fetus, watching as it developed from a tiny cluster of cells into a recognizable human form. And in the 1980s and 90s, researchers studying these grainy black and white images began to notice something fascinating. Let's watch a fetus at around 15 weeks of gestation. It is already remarkably active. Its tiny arms, barely a few inches long, are moving. Its miniature hands are opening and closing. Most importantly, it is frequently bringing its hands to its mouth. This is a foundational, instinctual behavior. And as scientists meticulously logged these movements, hour after hour, a clear pattern emerged. The movements were not random. A distinct majority of the fetuses showed a clear and consistent preference for putting one specific thumb in their mouth. And that thumb was, overwhelmingly, the right one. The statistics from these early studies were startlingly familiar. Somewhere between 85 and 90% of the fetuses preferred their right thumb, a number that perfectly mirrors the global rate of right-handedness in the adult population. This was a groundbreaking discovery. It was the first piece of scientific evidence that our hand preference begins long before we are born. But the most powerful part of this research came years later in the follow-up studies. The same researchers tracked down these children after they were born, at age 10, 12, and beyond, and tested their handedness. The results were astonishing. The preference a fetus showed for sucking one thumb at just 15 weeks. Gestation was a remarkably accurate predictor of the hand they would use to write and throw with a decade later. This finding effectively settled the nature versus nurture debate. While culture and training can certainly reinforce, or, in some historical cases, even suppress a person's natural inclination, the fundamental bias is there from the beginning. We don't learn our handedness from the world. We bring it with us into the world. The precise mechanism that kicks off this early preference is still a subject of intense research. Developmental biologists still debate the precise trigger for this early asymmetry. Is it a slight difference in gene expression, a hormonal fluctuation in the womb, or, as some recent fascinating research suggests, a subtle variation in the development of the spinal cord that emerges even before the brain's motor cortex is fully connected? Whatever the initial spark, the fire is lit in the quiet darkness of the second trimester, a silent choice that will shape how we interact with the world for the rest of our lives. Our journey has led us from ancient bones to the living brain, and from the living brain to the quiet, hidden world of the womb. We've established that our hand preference is not a learned behavior, but a biological trait, a choice made for us long before we are born. This conclusion leads us to one final fundamental question. Where are the instructions? If this preference is innate, it must be written into our genetic code, the DNA blueprint that builds us from a single cell. For decades, scientists went on a hunt for the handedness gene, hoping to find a simple, elegant piece of code with two variations, or alleles, one for right and one for left. The model was based on the simple Mendelian genetics we all learn in high school, like the genes for eye color or attached earlobes. It was a logical search, but it turned out to be a fruitless one. The handedness gene does not exist. The reason for this is that handedness is not a simple on or off trait. It is what geneticists call a polygenic trait, which is a far more complex and common type of inheritance. Instead of being controlled by a single gene, a polygenic trait is influenced by the combined effect of many different genes, each one providing a small, subtle nudge in a certain direction. Think of it less like a single light switch and more like a vast sound mixing board with hundreds of tiny sliders. Each slider makes a minuscule adjustment to the final sound. Your final handedness is the result of all those tiny genetic adjustments, combined with random developmental factors and environmental influences in the womb. This is the mainstream scientific fact of handedness genetics. It's a team effort. While we haven't found a single gene, researchers have identified several promising candidates that play a role in this genetic orchestra. One such gene is called PCSK6. This gene is not a handedness gene in the direct sense. Rather, it's a master architect of the body's overall asymmetry. It's part of the molecular machinery that, in the earliest stages of embryonic development, helps determine that your heart will be on the left side of your chest, your liver on the right, and your stomach on the left. This proper arrangement of organs is known as situs solitus, and it's a fundamental aspect of our body plan. It seems the same genetic toolkit that prevents the chaos of our organs being randomly placed also helps initiate the asymmetry in our developing brain. Other genes, like LRRTM1, have been more directly linked to the development of the brain's hemispheres themselves, influencing which side becomes dominant for certain tasks. The key insight here is that these genes don't seem to code specifically for right-handedness. Instead, their primary job appears to be to break the default state of perfect symmetry in the developing embryo. They provide a gentle probabilistic nudge that makes a right-handed outcome more likely, but not guaranteed. It's like tilting a perfectly level pinball machine ever so slightly to one side. Most of the balls will now fall to that side, but random chance and other small factors will still allow a few balls to end up on the other. This explains why even identical twins, who share the exact same DNA, do not always have the same handedness. Geneticists are still working to create a complete map of all the genes that contribute to handedness, and they debate the relative importance of these genetic factors versus random developmental events in the womb. But the overall picture is clear. The genetic blueprint is not a rigid command, but a subtle suggestion, a complex recipe that produces a consistent result most, but not all, of the time. We've completed a deep dive into the internal mechanisms of handedness, tracing the preference from the specialized hemispheres of the brain, right down to the subtle genetic recipe that nudges us in a right-handed direction from within the womb. We've answered the how, but now we must pull back, zooming out from the microscopic scale of DNA to the vast, grand stage of deep time to answer the more fundamental question: why? Why did this system evolve in the first place? What was the evolutionary problem that extreme handedness was the solution to? To find that answer, we must rewind the clock past the Neanderthals, past Homo heidelbergensis, past even the first stone tools of Homo habilis. We must go back to the very dawn of the human lineage, to a pivotal and revolutionary change that set our ancestors on a completely different path from all other apes. We have to go back to the moment we stood up. For tens of millions of years, our primate ancestors, like modern chimpanzees and gorillas, were primarily quadrupeds. They moved through the world on 4 limbs. Their hands were just as crucial for locomotion as their feet, bearing weight as they knuckle-walked across the forest floor. But somewhere between 4 and 6 million years ago, in the changing landscapes of Africa, our ancestors did something radical. They began to walk upright, on 2 legs. This is the defining trait of our lineage, the hominins. The famous 3.2 million-year-old fossil Lucy was a biped, and the even older Latoli footprints in Tanzania show us a poignant 3.6 million-year-old snapshot of 2 or 3 of our ancestors walking upright across a plain of volcanic ash. This shift to bipedalism was the single most consequential event in our entire evolutionary history. Paleoanthropologists still debate the primary catalyst for bipedalism. Was it to see over tall grass on the savanna, to free the hands for carrying food, or to more efficiently regulate body temperature in a hot climate? Whatever the initial driver, the consequence was revolutionary. For the first time, the hands were liberated from the mundane, repetitive job of walking. They were unemployed. This sudden freedom opened up an entirely new evolutionary arena, a space for natural selection to begin experimenting with manual dexterity in a way that was impossible for any other ape. The hands were now available, full-time, for a whole new suite of behaviors: carrying precious food back to a mate or offspring, holding and caring for a vulnerable infant, gesturing to communicate, and eventually picking up and manipulating objects from the environment. You can think of it like a company that has 2 of its most brilliant and versatile employees stuck working on a slow, monotonous assembly line. For millions of years, that's all they do. Then, one day, a management change, bipedalism, automates the assembly line and frees up those 2 employees. The CEO, natural selection, can now assign them to complex, high-value tasks in research and development, tasks that will ultimately transform the entire company. That's what happened to our hands. Once freed from the constraints of locomotion, they became the primary way our ancestors interacted with and manipulated the world. This, in turn, placed new and powerful demands on the brain. An individual with slightly better fine motor control, a slightly more precise grip, or a brain better able to coordinate hand and eye would have had a distinct survival advantage. Bipedalism did not cause right-handedness, but it was the essential, non-negotiable first step. It opened the door, and through that door walked an ancestor whose hands were now free to change the world, and whose brain would have to change right along with them. Our ancestors were on their feet. Their hands, newly liberated from the burden of locomotion, were now free to explore, to carry, to gesture. This was a moment of immense evolutionary potential. But potential needs a catalyst, a spark to ignite it into a roaring fire. That spark came in the form of a simple yet world-altering invention: the first stone tool. The creation of this tool did not just trigger a change. It initiated a powerful, self-reinforcing cycle, a positive feedback loop that would become the primary engine of human evolution for the next 2 million years. This loop inextricably linked our hands, our diet, and the very structure of our brains, driving them all forward in a cascade of accelerating change. Let's break down how this engine worked. It begins with a single act of creation. Imagine an early hominin, a Homo habilis on the African savanna. They are trying to create a sharp edge on a stone. At first, they might be clumsy, using both hands with equal inefficiency. But soon, a subtle preference emerges. They find that by holding the core stone steady in their left hand and using their right hand to deliver the precise, glancing blow with a hammerstone, they get a better result. The left hand becomes the stabilizing anchor, the right hand the dynamic actor. This small specialization leads to a slightly better tool, a flake with a sharper, more durable edge. This is the first step in the loop. A nascent hand preference leads to more efficient tool making. Step 2 is the reward. What do you do with a better tool? You get better food. These first tools were not primarily hunting weapons for taking down large game. They were butcher's knives. They were a ticket to a massive, untapped source of calories on the savannah. Large animal carcasses. With a sharp stone flake, our ancestor could now do something no other primate could. Slice through the thick, tough hide of a wildebeest or an antelope left behind by a lion. Even more importantly, with a heavy chopper, they could smash open the long bones to get at the prize inside, the incredibly rich, fatty, calorie-dense bone marrow. This was a nutritional jackpot, a superfood that provided the protein and lipids essential for building a hungry, growing brain. This leads to step 3, the investment. Brains are spectacularly expensive organs. Your brain, right now, while making up only about 2% of your body weight, is consuming around 20% of your daily caloric intake. For evolution to afford the cost of a bigger, more powerful brain, it needed a rich, reliable source of energy. The shift to a diet that included meat and marrow, made possible by stone tools, was the crucial financing plan for this expensive neurological project. The nutritional reward from better tools was invested directly into growing a larger, more complex brain. And this brings us to the final step, which closes the loop. A bigger brain is not just more of the same, it's a reorganized, upgraded machine. As the brain expanded, it came under pressure to become more efficient. One way to do this is through specialization, or lateralization. Instead of having redundant motor control circuits for complex tasks in both hemispheres, it's more efficient to consolidate them in one. The pressure for even greater tool-making skill would have favored brains that concentrated this fine motor planning in the left hemisphere. This enhanced specialization, in turn, allowed that hemisphere to direct the right hand with even greater speed and precision. A better brain made a better right hand, which could then make an even better tool. The loop was complete. Now, imagine this cycle turning not once, but over and over again, for 100,000 generations. Anthropologists still debate the exact sequence of this feedback loop. Did a larger brain enable the first tools, or did the invention of tools provide the nutritional resources that allowed for a larger brain? Regardless of which came first, once the engine started, it drove our lineage in a direction no other animal has ever taken. The engine was running. The feedback loop between tools, food, and brains was driving our lineage toward a future of unprecedented intelligence and dexterity. This explains why a specialized, dominant hand would have been an incredible evolutionary advantage. But it leaves us with a nagging question, a crucial piece of the puzzle that is still missing. Why the right hand? The logic of the feedback loop would work just as well if it had favored the left hand. Why didn't evolution produce a species that was roughly 50% right-handed and 50% left-handed? A coin toss of specialization. Why, instead, did our entire lineage, from Homo habilis onwards, converge on this one, single, consistent answer? The preference is so universal that it suggests there must have been some pre-existing condition, some subtle initial asymmetry that tipped the scales and sent us down the right-handed path. The answer, it seems, may not be found in our hands at all, but in how we see the world. Our hands, for all their skill, are ultimately just puppets. The real work is done by the brain that directs them, and that brain, in turn, is guided by the eyes. To understand why the left hemisphere was chosen for the job of fine motor control, we need to understand how it processes visual information. When light enters your eyes, the signal travels to the visual cortex at the very back of your brain. From there, the information splits and travels forward along two distinct pathways, or streams. Neuroscientists call these the dorsal and ventral streams. Think of them as two different kinds of visual analysis happening in parallel. The first, the dorsal stream, or the where pathway, flows upward. It is primarily concerned with spatial information, an object's location, its movement, its position relative to your body. It's the system that lets you reach out and grab a cup without consciously thinking about the distance or trajectory. This pathway is generally dominant in your right hemisphere. It sees the world in terms of relationships, context, and the big picture. Now, the second pathway, the ventral stream, or the what pathway, flows downward. Its job is identification. It focuses on the fine details, the texture, the color, the specific features that allow you to recognize an object for what it is. This is the stream that can tell the difference between a pebble and a walnut, between a friendly face and a threatening one. And this pathway is generally dominant in your left hemisphere. Here, then, is the crux of the theory. The demanding, difficult task of making a stone tool is overwhelmingly a what pathway problem. To be a skilled flint knapper, you need to be a master of seeing detail. You have to identify the subtle fissures and crystalline structures in the rock. You must focus on the precise, millimeter-perfect spot you need to strike. You must analyze the fine edge of the flake you just removed to decide on your next move. It is a task that requires your brain's high-frequency, high-definition visual processing power. And that processing power was already, for reasons deep in our primate past, slightly more developed in the left hemisphere. So, when the evolutionary pressure for better tool-making began to mount, the left hemisphere had a pre-existing advantage. It was already the brain's resident expert in seeing detail. It was simply more neurologically efficient to assign the job of directing the detailed action to the hemisphere that was already seeing the details. Keeping the expert seer and the expert doer in the same hemisphere minimized the processing lag and created a faster, more integrated system. The right hand, being the puppet of the left hemisphere, became the beneficiary of this ancient visual bias. The choice wasn't random. It was a logical consequence of how our brains were already wired to see. So far, our explanation has focused on the individual. We've explored how a specialized brain hemisphere made for a more efficient toolmaker, and how a pre-existing bias in the visual system likely favored the left hemisphere for this job. But this explanation, as compelling as it is missing a crucial element. Evolution does not just operate on individuals, it operates on individuals within groups. And our ancestors, like us, were intensely social creatures. They lived, worked, and survived in small, tightly knit cooperative bands. This social environment creates its own powerful set of evolutionary pressures. For a trait to become as universal as our 90-10 split, it must have offered more than just a personal advantage. It needed to benefit the entire group. The near-universal preference for the right hand may be the result of an unspoken, evolutionary social contract. Think about a world that is a 50-50 split of lefties and righties. On the surface, it seems perfectly fair and balanced. But in practice, it's a world filled with constant, tiny moments of friction and inefficiency. It's a world where every interaction requires a small but significant mental translation. Now, consider a world where almost everyone is the same. It's a world that is more predictable, more synchronized, and where crucial skills can be passed on with greater speed and fidelity. This is the core of the social hypothesis for handedness. The most powerful argument for this lies in the act of teaching. Imagine an experienced elder teaching a child how to knap flint. If the elder is right-handed and the child is left-handed, the child cannot simply imitate the elder's actions directly. To copy the movements, the child has to perform a complex mental rotation, mirroring the action as if looking in a mirror. This is neurologically demanding and can make learning a complex motor skill much more difficult. But if both the teacher and the student are right-handed, the child can sit beside or across from the elder and directly copy the movements, angle for angle, blow for blow. The learning process is intuitive, seamless, and far more efficient. In a prehistoric world where mastering tool-making was a matter of life and death, a population-wide standard for handedness would have acted as a powerful cultural accelerator, ensuring that vital skills were transmitted from one generation to the next with minimal error. This principle of predictability extends to other cooperative actions. While early tools were simple enough for anyone to use, later technologies may have been more specialized. A scraper might be flaked to fit perfectly in a right hand. A spear might be balanced for a right-handed throw. A common handedness creates a standardized toolkit, making the sharing of tools within a group more practical. Think of the simple frustration a left-hander feels today when trying to use a pair of right-handed scissors. Now imagine that frustration in a context where the tool is essential for your next meal, and consider the chaos of a coordinated group hunt. Predictability is paramount when you have multiple individuals moving quickly with sharp objects. If everyone in the hunting party throws their spear with their right hand, their movements are synchronized and easier to anticipate. It makes the group more effective as a unit and, crucially, safer for its members. Sociologists and anthropologists still debate whether the pressure for efficient teaching of tool-making skills or the need for coordinated action in hunting was the more powerful force in standardizing handedness across the entire population. But the underlying principle is the same. A common standard, an unspoken agreement to do things the same way, reduced cognitive load and increased group cohesion, providing a subtle but persistent advantage to the entire community. The need for a predictable, cooperative social world helps explain why a single-hand preference would spread throughout an entire population. But there is another, even more powerful social force that may have played a defining role in this story, a force that is arguably the very essence of what makes us human: language. We've already seen that the brain's primary centers for both producing and understanding language reside in the left hemisphere, in the very same neighborhood as the systems for controlling the hands. We have to ask the question, is that just a coincidence? Is it a simple matter of efficient brain packing, like putting the kitchen and the dining room next to each other in a house? Or is it a clue to a much deeper and more intimate connection between how we speak and how we act? An increasing number of scientists believe it is the latter, and their reasoning takes us back to the very origins of language itself. The theory is known as the gestural theory of language origin. It proposes that before our ancestors ever spoke a word, they had rich, complex conversations using their hands. Think about it. Our closest primate relatives, chimpanzees and bonobos, already use a wide variety of meaningful hand gestures to communicate. It is a plausible and logical starting point for our own linguistic journey. The theory suggests a clear evolutionary sequence, a series of steps that elegantly ties together bipedalism, gesture, and the specialization of the brain. It begins, as so many of our stories do, with us getting up on 2 feet. This act freed the hands, not just for tool use, but for communication. In a world without complex language, the hands become an incredibly versatile broadcasting system. You can use them to point to a distant predator, to mimic the shape of an animal you hunted, to describe the path to a water source, or to beg for a share of food. As these gestural conversations became more complex and nuanced, they would have placed the same kind of evolutionary pressure on the brain as tool-making did. It would have favored a brain that was better at producing and understanding rapid, ordered sequences of meaningful movements. And as we've seen, the left hemisphere was already predisposed to be the master of sequence. So, it became the natural hub for this emerging gestural language. The evidence for this is not just theoretical. You can feel it in your own behavior. Notice how you almost instinctively use your hands when you talk. We gesture to add emphasis, to describe a shape, to map out a timeline. We do it even when the person we're talking to can't see us, like when we're on the phone. This is a kind of fossil behavior, a deeply ingrained remnant of a time when the hands were the primary vehicle for our thoughts. The most compelling evidence, however, is that shared neurology. The fact that Broca's area controls the motor planning for the hands, face, and the mouth is no accident. It's the brain's unified communication center. According to the theory, vocalizations came later. As our vocal tracts evolved to allow for a finer range of sounds, speech began to piggyback on the sophisticated grammatical framework that the left hemisphere had already built for gesture. The brain essentially mapped the new sounds of speech onto the older, pre-existing structure of hand signs. And if this theory is correct, it has a profound implication for our mystery. If the left hemisphere evolved to become the engine of communication, first for gesture and then for speech, then the right hand it controls would have naturally become the primary speaking hand. It would have become the more articulate, practiced, and dominant hand for conveying meaning. In this view, our right-handedness is a direct physical consequence of our evolution as social communicating beings. Linguists and paleoanthropologists are still locked in a fascinating debate about the takeover process. Was the shift to vocalization gradual, with gesture and speech coexisting for a long time, or was it a more rapid revolutionary switch? Regardless, the theory presents a powerful idea. Our handedness is the silent echo of our ancestors' first conversations. We've explored the grand, powerful forces that may have shaped our handedness, the intellectual demands of tool-making, the social necessity of teaching, and the communicative dance of gesture. These are the loud, dramatic scenes in our evolutionary play. But evolution is also driven by quieter, more subtle pressures, by behaviors that are so constant and fundamental, they are like the background rhythm of existence. We're going to turn now to one of the most fundamental of all hominin behaviors, a task that has been a constant for millions of years, the simple, profound act of carrying an infant. This has led to a fascinating and gentle explanation for our right-hand bias, known as the maternal heartbeat hypothesis. The theory begins with a simple observation. Picture a parent comforting a baby. On which side of their body are they most likely to be holding the child? For decades, observers noticed a distinct tendency for mothers, regardless of their own handedness, to cradle their infants on their left side. This wasn't just a folk tale. It was a real, observable phenomenon across numerous cultures. For a long time, it was assumed this was simply for convenience. If you're right-handed, you hold the baby with your left arm to keep your dominant hand free. But the bias also appeared in left-handed mothers, which suggested something deeper was at play. The proposed reason is both beautiful and powerfully simple. Holding an infant on the left side of your chest places the baby's head and ear directly over the steady, rhythmic beat of your heart. Lub-dub, lub-dub. This is not just any sound. It is the first and most constant sound an infant ever hears, the reassuring percussion of its 9-month existence in the womb. After birth, in a world that is suddenly loud, bright, and overwhelming, the sound of the maternal heartbeat is a powerful and familiar source of comfort and security. It has a documented calming effect on infants, regulating their breathing and reducing crying. A mother who instinctively holds her baby on the left is providing a constant stream of this natural tranquilizer. This isn't just a human quirk. Scientific studies have shown that this left cradling bias exists in our closest relatives as well, including chimpanzees, gorillas, and orangutans, suggesting it is a deep-seated primate instinct, not a learned cultural behavior. An ancestral mother who calmed her infant more effectively would have had a quieter, less stressed, and thus less vulnerable child, a subtle but significant survival advantage. And here is the crucial link to our story. If our female ancestors, for millions of years, had a strong instinct to hold their precious, helpless offspring with their left arm against their heart, then their right arm and hand were, by necessity, a lot freer. The right hand became the go-to limb for every other task. It was the hand used to gather berries and dig for roots while the baby was being held. It was the hand used to carry a digging stick or a primitive tool. It was the hand used to gesture to others, to swat away insects, or to steady herself on a branch. This would have created a persistent, gentle, yet unrelenting evolutionary pressure for the right hand to become the more dexterous, practiced, and versatile appendage, particularly among the female population. Evolutionary biologists debate whether this subtle, maternal pressure would have been strong enough on its own to drive handedness, or if it was more likely a contributing factor that reinforced the biases already being created by tool use and gesture. Regardless, it adds a wonderfully intimate layer to our story, suggesting that our species' preference for the right hand may have been shaped not only in the noisy, flint-knapping workshops of our ancestors, but also in the quiet, tender, and protective embrace of a mother and her child. We have spent our entire journey so far deep within our own family album, looking at the traits of our parents, grandparents, and extinct cousins in the hominin lineage. We've built a strong case that our right-handedness is the result of a unique cocktail of evolutionary ingredients: bipedalism, tool use, social learning, language, and perhaps even the gentle rhythm of a mother's heart. But to truly appreciate what makes a story unique, you have to read other books. To understand our own path, we must look sideways at the paths taken by the countless other species we share this planet with. Is this profound bias for one side of the body a common evolutionary strategy? Or is it another trait that makes our lineage peculiar? For a very long time, Handedness was thought to be one of the defining features of humanity, a clear line in the sand between us and the animal kingdom. We now know that this is not true. The animal world is full of lefts and rights, of individual and even group-level preferences. But these examples, in their fascinating variety, ultimately serve to highlight just how strange our own 90-10 split really is. Let's travel to the sun-scorched plains of Australia, where we can observe one of the most remarkable and revealing cases of animal-handedness. You watch a red kangaroo as it browses. It stands upright, balanced on its powerful hind legs and thick tail, a posture that, like our own bipedalism, frees its forelimbs for other tasks. As you observe, you notice it reaching out to bend a branch down to its mouth, and it uses its left paw. A moment later, it grooms its long snout, and again, it is the left paw that does the delicate work. This is not an isolated incident. Scientific studies have confirmed that many species of kangaroos and wallabies exhibit a striking population-level preference for their left paw, especially for tasks that require fine motor control. This is a stunning example of convergent evolution, a completely different lineage of mammals, faced with the same biomechanical situation, freed forelimbs thanks to an upright posture, also evolved a species-wide hand preference. It's a powerful confirmation that bipedalism is a key ingredient in the recipe for handedness. But the kangaroos threw a fascinating twist into the story. They chose the left. This is incredibly important. It proves that simply standing up does not automatically lead to a right-hand preference. It tells us that the specific evolutionary path our ancestors took, the one that tied detailed visual processing and tool-making to the left hemisphere, was not the only option available. The kangaroo's left-handedness is a perfect natural experiment that reinforces the uniqueness of our own right-handed journey. The world is filled with other, more subtle examples. Many species of parrots, for instance, are distinctly footed. They will almost always use one preferred foot, either the left or the right, to grasp a piece of food and bring it to their beak, much as we would use a preferred hand to hold a fork. Even in the ocean, we see lateralized behavior. Gray whales, as they feed, will often roll onto their side to scoop up sediment from the ocean floor, filtering out crustaceans and other small creatures. Examinations of beached whales have shown that for many individuals, the right side of their jaw and their filtering baleen are significantly more worn down, indicating a lifetime of right-sided feeding. Biologists are still investigating the evolutionary advantages of these preferences. Is the whale's choice linked to hemispheric specialization for navigating ocean currents while feeding? Or is it a random evolutionary artifact? From the paw a toad uses to wipe its face to the eye. A fish prefers to use to watch a predator. A preference for one side of the body is a common evolutionary trick. But as we are about to see, no other species has taken this trick to the extreme population-level uniformity that we have. We have taken a brief but fascinating detour through the wider animal kingdom. We've seen left-pawed kangaroos, right-jawed whales, and footed parrots. The evidence is clear. Having a preferred side is not an exclusive human club. This widespread phenomenon, known to scientists as lateralized behavior, seems to be a common evolutionary strategy. It's a sensible bit of biological design. By assigning different tasks to different brain hemispheres, you avoid duplicating effort, you can process information in parallel, and you can increase the speed and efficiency of your actions. Evolution, it seems, stumbled upon this trick many times in many different lineages. Acknowledging this, however, brings us to the most important question of all. If having a preferred side is common, What, if anything, makes the human situation special? The answer is not in the preference itself, but in the overwhelming species-wide consensus. Let's return to our example of the parrots. While many individual parrots have a strong preference for one foot, if you were to survey the entire global population of a given parrot species, you would likely find a roughly 50-50 split between left-footed and right-footed individuals. The species as a whole is balanced. The same is true for our closest living relatives, chimpanzees. While any single chimp might prefer to use its right hand for termite fishing or its left for throwing, the overall population shows no significant bias in either direction. For every right-handed chimp, there is, somewhere out there, a left-handed one. Theirs is a world of individual preference. Ours is not. This is the crucial distinction that sets us apart. If you survey 1,000 humans, from Paris, from Patagonia, from Papua New Guinea, you will find that around 900 of them are right-handed. This isn't balance. This is a profound and powerful population-level skew that has been maintained across cultures and across continents for millions of years. No other species on Earth exhibits such a strong, consistent, and lopsided bias for one side of the body. While other animals whisper a preference, our species shouts it. The reason for this uniqueness lies in the perfect storm of evolutionary pressures that we have spent our journey exploring. It was not one single factor, but a unique combination of them, all converging and pushing in the same direction. Our bipedalism freed the hands, a trait we share with kangaroos. But unlike kangaroos, our freed hands were then put to work by a brain that was developing an unprecedented capacity for complex, sequential tool-making guided by a highly detailed visual system. This practical pressure was then amplified by our intensely social nature. The need to teach these complex skills and coordinate group activities favored a population-level standard. And this was likely intertwined with the evolution of language, as the left hemisphere became the hub for a communication system that may have begun with the hands themselves. Evolutionary anthropologists continue to debate which of these factors was the true tipping point that pushed our lineage from a balanced 50-50 preference to the extreme 90-10 skew we see today. Was it the invention of the first complex hand axe, or the dawn of symbolic language? Whatever the final catalyst, the result was extraordinary. We became not just a species of tool makers and talkers, but a species of overwhelmingly right-handed tool makers and talkers. This now leaves us with the final and perhaps most intriguing part of our mystery. If the evolutionary current toward right-handedness was so powerful, how did anyone manage to swim against it? Why are there any left-handers at all? We have arrived at what seems to be a closed case. We have followed a chain of reasoning, supported by fossils, archaeology, and neuroscience, that presents an overwhelming argument for why our species became right-handed. The freedom of bipedalism, the demands of tool-making, the efficiency of social learning, the neurology of language, all these powerful evolutionary currents converged, creating a torrent that should have pushed our entire population onto the right-handed bank. When a trait is this advantageous, the normal course of evolution is for it to spread until it becomes universal, a process called fixation. The genes and developmental pathways that produce the advantageous trait are selected for, generation after generation, until the alternative version is completely eliminated. By this logic, left-handedness should be an evolutionary relic, a trait that disappeared from our gene pool hundreds of thousands of years ago. And yet, here you are, or here your friend, your sibling, your parent is. 1 in 10 people listening to this right now is a living, breathing paradox. The southpaw, the lefty, the 10%. They persist. They are a constant and stable minority in every population on Earth. The fact that left-handedness has not been eliminated is not an evolutionary oversight. It is a clear and powerful signal that our story is more complex than it appears. It tells us that being a left-hander, despite all the pressures for conformity, must also carry its own unique and powerful evolutionary advantage. The system isn't broken, it's balanced. This phenomenon is known to biologists as balancing selection. It's a situation where natural selection actively maintains multiple different versions of a trait within a population. One of the most common ways this happens is through a mechanism with a rather complicated-sounding name: negative frequency-dependent selection. But the idea behind the name is actually quite simple and elegant. It just means that a trait's fitness, its evolutionary advantage, is negatively dependent on how common or frequent it is. In other words, the rarer a trait is, the more advantageous it becomes. Imagine a population of prey animals, like gazelles, being hunted by cheetahs. Let's say 90% of the gazelles have an instinct to dodge to the right when a cheetah attacks. The cheetahs, through experience, learn to anticipate this, and they become very good at catching the right-dodging gazelles. But the 10% of gazelles with a rare genetic variant that makes them dodge to the left have a huge advantage. Their move is unexpected. The cheetah zigs right, the gazelle zags left, and escapes. In this environment, being the odd one out, being the lefty, is a winning strategy. But what would happen if, over many generations, the left-dodging gazelles became more and more common? The advantage would disappear. If the population became 90% left dodgers, the cheetahs would simply adapt and start anticipating a left dodge, and the rare right dodgers would now have the advantage. This dynamic creates a stable balance, where the rare lefty trait is preserved at a low but consistent frequency because its advantage depends entirely on it being a surprise. This is almost certainly the dynamic that has kept left-handedness as a permanent part of the human story. Being a lefty in a world overwhelmingly designed for and populated by right-handers must have provided a significant strategic edge in certain types of encounters, an edge so powerful that it was enough to counteract the immense pressure to conform. The existence of the southpaw isn't an accident, it's a strategy. So what is the strategic advantage of being a lefty? An advantage so potent that it has kept the trait alive for millions of years against a powerful evolutionary tide. The most widely accepted answer is simple, visceral, and brutally effective: fighting. The theory is known as the fighter's advantage hypothesis, and it posits that in any hostile one-on-one confrontation, the individual with the rarer phenotype holds a distinct and often decisive edge. This is the real-world scenario where the gazelle's unexpected left dodge plays out in human form, a surprise tactic that evolution has seen fit to keep in its arsenal. The logic is straightforward. Imagine you are a right-hander living in our ancestral world. Roughly 9 out of every 10 people you ever get into a physical conflict with, whether a serious fight or a competitive struggle, will also be right-handed. Your entire life, your reflexes, your muscle memory, and the predictive models in your brain are being trained and optimized to defend against attacks coming from a right-handed opponent. You learn to anticipate the angle of a club's swing, the arc of a punch, the lunge of a spear, all from a right-handed stance. It becomes second nature. Then one day you face a southpaw. Suddenly, the entire script is flipped. The jab, which you expect from your opponent's left hand, now comes from their right. Their power hand, which should be in the back, is now in the front. Their footwork is a mirror image of what you're used to. Every angle is wrong. This creates a critical moment of cognitive dissonance. Your brain, trained on a lifetime of right-handed data, has to pause, recalculate, and adapt to this new, unfamiliar threat. In a violent encounter, a split second of hesitation can be the difference between success and failure. Now, consider the left-hander's perspective. They have spent their entire life sparring, competing, and fighting against right-handers. For them, this mirrored stance is not a surprise. It is the norm. They are the specialists in fighting the majority, while the majority are novices at fighting them. The advantage of surprise is a one-way street. This is not just a compelling theory. It is a statistically verifiable fact, borne out in the data from modern combat sports. These sports are, in essence, a ritualized and non-lethal echo of the kinds of individual conflicts our ancestors would have faced. If you look at the top ranks of interactive, one-on-one sports like boxing, fencing, and mixed martial arts, you will find left-handers are represented in far greater numbers than their 10% in the general population would predict. Studies have shown that left-handed boxers and MMA fighters win significantly more of their matches. The southpaw stance is notoriously difficult for orthodox fighters to deal with. Famous fighters like Manny Pacquiao have built legendary careers on this inherent advantage. In our prehistoric past, this was not about winning a title or a prize purse. It was about survival. A slight edge in a one-on-one conflict over resources, status, or a mate could directly translate into greater reproductive success. Historians and anthropologists debate just how much of a role individual combat played in the overall evolutionary fitness of early humans, compared to group cooperation and other survival skills, but its role was certainly not zero. This persistent life-or-death advantage was enough to ensure that the genes and developmental pathways that led to left-handedness were never erased. The southpaw was, in essence, evolution's secret weapon, a strategic diversity that made the human population as a whole more resilient and unpredictable. The fighter's advantage gives us a powerful, clear-cut reason for the persistence of the southpaw. The element of surprise is a potent weapon. But is that the entire story? Is the advantage purely one of external strategy, of simply being an unexpected opponent? Or could there be something fundamentally different about the internal wiring of a left-hander's brain that contributes to this advantage, and perhaps others? When we look inside the skull of a lefty, we find that their brain is often not just a mirror image of a right-hander's. It is, in many cases, a differently organized system, a brain built on a philosophy of integration rather than strict specialization. We have spent much of our journey exploring the concept of brain lateralization, the sharp division of labor between the left and right hemispheres that defines the typical right-handed brain. We saw how the left hemisphere became the specialist for language and sequential tool use. In many left-handers, however, this division of labor is less pronounced. Their neurological functions tend to be more evenly distributed across both hemispheres. For example, while over 95% of right-handers have their primary language centers in the left hemisphere, this is only true for about 70% of left-handers. For the other 30%, language is either controlled by the right hemisphere or, most commonly, spread more bilaterally across both. This more symmetrical, less specialized brain organization is the mainstream neurological finding for left-handers. This whole brain approach to processing is made possible by the physical connection between the two hemispheres, a massive C-shaped bundle of over 200 million nerve fibers called the corpus callosum. Think of it as the superhighway of your brain, the data cable that allows your two specialized department heads to be in constant communication. And here, we find another subtle but significant difference. Neuroscientists are still actively debating the consistency of the findings regarding the corpus callosum, with some studies showing a clear size difference and others finding none, suggesting the relationship is complex and not true for all left-handers. However, a compelling body of research suggests that this structure can be larger or differently organized in left-handers, allowing for a higher bandwidth of information to flow between the hemispheres. What are the potential benefits of this integrated, well-connected brain? For one, it offers a remarkable resilience to injury. If a right-hander suffers a stroke that damages the language centers in their left hemisphere, the effect can be devastating and permanent. Because their linguistic skills are so heavily concentrated in one spot, there's no backup system. In a left-hander with more distributed language functions, the healthy hemisphere can often take over and compensate, leading to a much faster and more complete recovery of speech. This is a profound survival advantage. And in the heat of a conflict, could this enhanced crosstalk provide a split-second edge? Perhaps the right hemisphere's superior spatial awareness can communicate more rapidly with the motor planning centers, regardless of which hemisphere they are in, leading to faster and more fluid reactions to an opponent's movements. Beyond physical advantages, this different wiring diagram may allow left-handers to approach problems in a unique way, to literally think differently by more easily combining the specialized processing styles of both hemispheres. It's a brain built not for rigid division, but for flexible collaboration. The idea of a differently wired, more integrated brain leads us directly to one of the most enduring and romantic stereotypes about left-handers. It is the archetype of the creative genius, the eccentric artist, the innovative thinker who sees the world from a unique angle. We picture the left-handed musician, painter, or scientist, whose different way of thinking allows them to make intuitive leaps that the more conventional, right-handed mind might miss. It's a compelling image, but is there any scientific truth behind it? Does the Southpaw's differently organized brain actually make them more creative? This question is the subject of a long-standing and fascinating scientific puzzle. The link between left-handedness and creativity is a topic of intense study and argument, with some studies showing a positive correlation and others finding no significant link. It is not a settled science, but a tantalizing field of inquiry. The theory for why a connection might exist, however, is grounded in the unique neurology we've just discussed. If creativity, at its core, is about making novel connections between existing ideas, then a brain that is built for connection should, in theory, have an advantage. The hypothesis is that the left-hander's more robust corpus callosum and more integrated hemispheres allow for a greater degree of crosstalk between different modes of thought. Think of the specialized toolkits of the two hemispheres. The left brain excels at analytical, logical, and sequential processing, pulling things apart to see how they work. The right brain excels at holistic, spatial, and intuitive processing, seeing the big picture and understanding context. A right-hander's brain, with its strong division of labor, might approach a problem by primarily using one toolkit or the other. The theory suggests that a left-hander's brain can more easily and rapidly blend the two. They can simultaneously see the intricate details and the overarching pattern, the logical structure and the intuitive leap. This ability to synthesize different ways of thinking is the very definition of divergent thinking, a key psychological marker of creativity. It's the ability to look at a familiar problem and generate a multitude of new, unconventional solutions. History certainly provides us with a compelling, if anecdotal, list of left-handed innovators. Leonardo da Vinci, the ultimate Renaissance man, famously wrote his notes in a left-handed mirror script. Michelangelo, Marie Curie, and Isaac Newton are all believed to have been left-handed. The list is long and impressive, and it seems to support the stereotype. However, we must be incredibly cautious with this kind of evidence. It's highly susceptible to confirmation bias. We celebrate the examples that fit the narrative, while conveniently ignoring the countless brilliant right-handers and the millions of perfectly ordinary left-handers. Furthermore, definitively determining the handedness of a historical figure is often a tricky and speculative business. The formal scientific evidence is equally complex. Some studies have indeed found that left-handers, as a group, tend to score higher on tests of divergent thinking. One study found that left-handers were significantly overrepresented in creative professions like art, music, and architecture. And yet, for every study that finds a link, another study finds no statistically significant difference at all. The truth is likely nuanced and complex. But while the science remains unsettled, the possibility is captivating. The left-hander's brain is a testament to the value of diversity. It reminds us that there is more than one way to wire a human mind, and this neurological variety may be a crucial ingredient in our species' remarkable capacity for innovation and art. We've just explored the subtle neurological advantages that may come with being left-handed: a more resilient and integrated brain, a potential edge in combat, and a tantalizing link to creative thinking. It's a compelling picture of a different but equally valid way of being human. And yet, for the vast majority of recorded history, the experience of being a left-hander was not one of strategic advantage or celebrated uniqueness. It was a story of suspicion, stigma, and a constant grinding pressure to conform to the right-handed world. The bias against the 10% is not just evolutionary. It is deeply and often cruelly cultural, a prejudice so old it is woven into the very words we speak. Language is a living fossil record of our beliefs and biases. To understand the historical plight of the left-hander, you need only look at our vocabulary. Consider the English word sinister. Today it means evil, ominous, or threatening. But the word is a direct import from Latin, where sinister simply meant left. The association is baked right into the etymology. Left is evil. The same is true in French, where the word gauche means left, but it also means awkward, clumsy, or socially inept. By contrast, words associated with the right hand are almost universally positive. The word right itself means correct, proper, and just. To be skillful is to be adroit, a word that comes from the French phrase à droite, meaning to the right. For centuries, our languages have been whispering a constant, subtle message: right is good and left is wrong. This linguistic bias is the symptom of a much deeper cultural and religious prejudice. Across countless societies, the left hand was historically designated as the unclean hand, the one reserved for personal hygiene, while the right hand was the clean hand was for eating, greeting, and all sacred or public acts. This division of clean and unclean, sacred and profane, was mapped directly onto the hands. In many religious traditions, this symbolism took on a cosmic significance. In Christian art and scripture, the righteous and the saved are seated on the right hand of God, while the damned are cast to the left. The devil himself was often depicted as being left-handed, a divine confirmation of the left's association with heresy and evil. This belief was so ingrained that during the infamous witch trials, being left-handed was sometimes used as evidence of a pact with dark forces. Even our minor superstitions echo this ancient bias. When you spill salt, you ward off the bad luck by tossing a pinch over your left shoulder into the eyes of the devil who is said to lurk there. This deep-seated stigma had profound and often painful consequences, especially for children. Well into the 20th century, in schools across Europe and North America, being left-handed was treated not as a natural variation, but as a flaw to be corrected. Teachers, believing they were acting in the child's best interest, would actively force naturally left-handed students to write with their right hands. The methods could be harsh: tying the child's left hand behind their back, rapping their knuckles with a ruler every time they reached for a pen with the wrong hand, and constant verbal shaming. This forced conversion, which we now know can cause a host of developmental issues, was born from a centuries-old belief that the left hand was, at best, a clumsy inconvenience, and at worst, a mark of deviance. So, while left-handedness may have conferred a subtle advantage in a prehistoric fight, for most of civilized history, it was a trait to be hidden, suppressed, and overcome. Thankfully, the overt and often brutal prejudice against the left hand has largely faded into history. In most modern societies, forcing a child to switch their writing hand is seen as an antiquated and harmful practice. The belief that left-handedness is a mark of deviance has been replaced by a scientific understanding of it as a natural neurological variation. But while the cultural stigma has receded, left-handers still live in a world that was not built for them. They are the 10% navigating a world physically designed by and for the 90% majority. This creates a lifetime of small, subtle, but ever-present frictions, a constant low-level negotiation with a material world that is oriented the wrong way. The challenges begin with one of the first fine motor skills we ever learn: writing. For a right-hander using a script that moves from left to right, like English, the process is natural. The hand pulls the pen across the page, moving away from the fresh ink, with a clear view of the words just written. For a left-hander, the entire dynamic is reversed. They must push the pen, an action that is less fluid and can cause the nib to dig into the paper. More frustratingly, their hand must drag directly over the line they have just written. For centuries, this meant a hand perpetually stained with the side of their palm covered in a smear of graphite or ink. This is the infamous smudge that every lefty knows. The simple spiral notebook becomes an obstacle course, its metal rings digging into the side of the writing hand. This design bias is everywhere, hidden in plain sight. Consider a simple pair of scissors. They appear symmetrical, but they are not. On a pair of right-handed scissors, the top blade is on the right, so the pressure of a right-handed grip pushes the two blades together, creating a clean shearing action. When a left-hander tries to use these same scissors, the physics are all wrong. The pressure from their left hand forces the blades apart. Instead of a crisp cut, the paper simply folds and gets chewed between the blades. To a left-hander, a normal pair of scissors feels broken, not because the tool is faulty, but because it was engineered for a different body. The kitchen is a museum of right-handed design. Most can openers are built to be held steady with the left hand while the right hand turns the crank. Measuring cups often have the measurement lines printed on the side that is only visible when you hold the handle in your left hand, assuming you will be pouring with your right. The modern workspace is no different. The computer mouse, especially an ergonomic one, is sculpted to the contours of a right hand. The number pad on a full-size keyboard is always on the right. Even our hobbies are biased. The shutter button on a camera, the safety switch on a power tool, the handle on a fishing reel, all are placed with the right-handed user as the default. Ergonomics experts and safety researchers still debate the extent to which this design bias contributes to higher accident rates for left-handers when using certain tools and machinery, though some studies suggest a measurable increase in risk. Any one of these inconveniences is a minor thing, but the cumulative effect of dozens of such tiny hurdles, day after day, creates a fundamentally different experience of the physical world. In response, a small but thriving market has emerged, a testament to the left-hander's plight. You can now buy left-handed scissors, notebooks with the spiral on the right, and even pens with curved barrels and quick-drying ink to finally defeat the smudge. It's a quiet acknowledgement that the world is, by default, a right-handed place. We have traced the long and winding evolutionary path of human-handedness from its deepest roots nearly 2 million years ago to the subtle inconveniences of the modern, right-handed world. We've seen the forces that created the 90-10 split, and the counterforces that have preserved it in a delicate balance. This brings us to our final question, a question not of the past, but of the future. Is this story over? Is the 90-10 ratio a stable, permanent feature of our species? Or are we, in our modern technological world, still evolving? Is the chapter on handedness still being written? If you were to look at a graph of handedness over the last century, you might be tempted to think that rapid evolution is indeed happening. In many Western countries, the reported percentage of left-handers rose steadily throughout the 20th century, from as low as 3% in the early 1900s to the 10 or 12% we are familiar with today. But this is not evidence of a sudden genetic shift. It is a cultural echo. This rise in left-handedness mirrors almost perfectly the decline of the harsh practice of forced switching in schools. As societal stigma faded and teachers put away their rulers, the true biological number of left-handers was simply allowed to reveal itself. We weren't evolving to become more left-handed. We were just stopping the process of suppressing them. But what about the genuine evolutionary pressures? Have they changed? The fighter's advantage, the primary theory for why left-handers are maintained in the population, was a matter of life and death for our ancestors. In the modern world, while the advantage is still statistically visible in sports, one-on-one combat is thankfully no longer a primary driver of reproductive success for most humans. The selective pressure that once kept the southpaw genes in circulation has almost certainly weakened. At the same time, the social pressures for conformity have also relaxed. In a small hunter-gatherer band, having a standardized way of making and using tools was crucial. In our globalized world of mass manufacturing and digital tutorials, the need for everyone to do things the same way has lessened considerably. Perhaps the most interesting new factor is our technology. For millions of years, our primary tools, from hand axes to spears to scissors, were designed for a single, dominant hand. But what are the defining tools of the 21st century? The keyboard, the game controller, the smartphone. These technologies are fundamentally different. They are largely symmetrical and often require the skilled and coordinated use of both hands. The dexterity required to type quickly or to operate a complex game controller is a two-handed skill. This new technological environment might be subtly changing the very definition of manual dexterity. The premium is no longer on the supreme specialization of one hand, but on the coordinated skill of two. So, where does that leave us? Evolutionary futurists and biologists debate whether the relaxed selection pressures of the modern world will cause the 90-to-10 ratio to drift randomly over the coming millennia, or if new pressures from technology will actively select for a different kind of manual dexterity altogether. It's a fascinating and open question. The 90-10 split has been one of the most enduring and stable features of the human lineage. It may be so deeply baked into our neurological and genetic makeup that it will remain with us for as long as we are human. Or we may be living at the very beginning of a new chapter, a time when the ancient clear-cut division between the right and the left hands begins, ever so slowly, to blur. Our journey is nearing its end. We have traveled from the sun-baked savannas of our earliest ancestors to the silent, painted caves of Ice Age Europe. We have peered inside the intricate wiring of the modern human brain and journeyed back to the quiet, dark world of the womb. We have followed a trail of clues left in fossilized teeth, ancient bones, and the very words we speak. Now it is time to assemble these pieces, to step back and see the grand, sweeping narrative they collectively tell. The story of how we became a right-handed species can be told as a great evolutionary play in 4 acts. Act 1 begins with the setting of the stage. Millions of years ago, our ancestors made a radical departure from the ape family tree. They stood up. This shift to bipedalism was the foundational event, the revolutionary change that liberated our hands from the drudgery of locomotion. For the first time, these marvelously versatile appendages were free, available for new and more complex work. This act did not determine our final destiny, but it opened the door of possibility. It created the evolutionary space for the hands to become the primary instruments through which we would engage with and ultimately reshape the world. Act 2 introduces the inciting incident, the invention of the stone tool. With their hands now free, our ancestors began to create. This sparked the powerful, self-reinforcing feedback loop that became the engine of our evolution. A slight preference for one hand led to better tools. Better tools meant access to better food, like meat and calorie-rich bone marrow. This high-quality nutrition, in turn, provided the immense amount of energy required to fuel the growth of a larger, more complex, and more metabolically expensive brain. It was a cycle of advancement where our technology and our biology pushed each other forward, step by step, for 100,000 generations. Act 3 shows the internal transformation. The growing brain, under the constant pressure to become more efficient at making tools and eventually at communicating, began to specialize. It adopted the strategy of lateralization, dividing its labor between the 2 hemispheres. The demanding sequential and detail-oriented tasks of language and complex tool-making were consolidated into one masterful hemisphere. Evidence from our visual processing systems and the neurology of gesture suggests that the left hemisphere had a pre-existing advantage for this role. It became our species' designated specialist for the tasks that would come to define us. This leads us to the final act, the inevitable conclusion. The right hand, being the limb directly controlled by the newly specialized left hemisphere, became the primary agent of our ancestors' will. It became the default hand for crafting a tool, for throwing a spear, for making a meaningful gesture. This individual preference was then locked in at the population level by the pressures of social living, where a common standard made teaching skills and coordinating actions far more efficient. The story that began with a simple change in posture culminates in a species whose very brains are wired to favor one hand, a preference that echoes down through the ages to the very moment you reached out to press play on this story. The 4-act play we just described gives our story a clean, linear structure, a satisfying sense of cause and effect. It is a good and useful summary of the main evolutionary plot. But the reality of any deep evolutionary story is always a little messier, a little more complex. The temptation, when faced with a profound mystery like human handedness, is to search for a single, elegant cause, a smoking gun that explains everything. We want to be able to say it was all because of tools, or all because of language, or all because of a single gene. But this is not how evolution works. The truth is that there is no single answer. Our profound bias for the right hand is not a sculpture carved by a single force, but a complex and beautiful mosaic, assembled piece by piece over millions of years by a host of different interacting pressures. To truly appreciate the answer to our question, you have to see all the different tiles of this mosaic at once. There is the deep, foundational tile of our evolutionary history, the shift to bipedalism that freed the hands and the powerful feedback loop between tool technology and our expanding brains. This is the bedrock on which the entire structure is built. Laid upon that is the intricate tile of our neurology, the way our brains, in their quest for efficiency, split their labor between two specialized hemispheres. This includes the subtle, pre-existing bias in our visual system that made the left hemisphere the expert at seeing detail, and the shared neural real estate for controlling both our hands and our language. Next to that is the subtle, multicolored tile of our genetics. This is not a simple blueprint with a single command, but a complex recipe with dozens, perhaps hundreds of genetic ingredients that collectively create a gentle, probabilistic nudge towards a right-sided outcome. Then there is the crucial tile of our development, the process by which that genetic suggestion is translated into a physical preference within the quiet, dark environment of the womb, a preference that is already established long before we are born. And finally, laid over all of these biological factors is the shimmering, protective tile of culture and society. The pressure in small ancestral groups for a common standard that made teaching and cooperation easier, a pressure that, for much of recorded history, twisted into a harsh stigma against the 10% who deviated from the norm. None of these pieces exists in isolation. They all interact, weaving together to form the final picture. The genetic recipe helps to build a brain that is predisposed to lateralize. That neurological structure is then shaped and honed by the evolutionary pressure of tool use. The skills developed for tool use are then passed on through social learning, which is made more efficient by the very population-level bias it helps to reinforce. It is a fully interconnected system. Think of it not as a single chain of events, but as a thick, powerful rope woven from many different strands. Each strand, genetic, developmental, neurological, social, contributes its own strength to the whole. Our right-handedness is the result of all these strands twisting together, pulling in the same general direction for 2 million years. We have assembled our mosaic. We have woven together the different strands of genetics, evolution, and culture to create a rich and complex story. It is the most complete story that science can tell us right now, and it's a deeply satisfying one. And yet, a truly great scientific story is not one that claims to have all the answers. It is one that is honest about the boundaries of its knowledge, one that is comfortable with mystery. The journey of discovery is never truly over. For all that we have learned about our handedness, there are still profound and fascinating questions that remain unanswered, blurry patches in our beautiful mosaic that are still waiting to be filled in. One of the deepest mysteries takes us back to the very beginning of our story, the primal tilt. We have a plausible explanation for why the left hemisphere was chosen for the job of language and tool-making. Its pre-existing specialty in processing fine-grained visual detail. But this just pushes the question back one step further. Why did the left hemisphere develop this visual specialty in the first place? What was the initial, tiny event deep in our primate past that broke the brain's perfect symmetry and set the two hemispheres on their different developmental paths? We do not know. Finding that first, subtle nudge that started the entire cascade of lateralization is one of the holy grails of neuroscience. The genetic story, too, is far from complete. We know that handedness is a polygenic trait, but we have only identified a handful of the possible candidate genes. The full genetic architecture is likely a breathtakingly complex network of hundreds of genes, each interacting with one another and with the environment in subtle ways. Creating a complete map of this network is a monumental task that is still in its infancy. We have the first few ingredients of the recipe, but the full cookbook, the one that can explain all the variations and subtleties of human-handedness, is still waiting to be written. And what of the left-hander's brain? We know that it is often a more integrated, less specialized system, but we are still wrestling with a classic chicken or the egg problem. Is a left-hander born with a more interconnected brain, a different neurological starting point that leads to their hand preference? Or does the brain become more interconnected as a result of a lifetime of adapting and navigating a world designed for the opposite hand? It's possible that the very act of being a lefty, of constantly having to use tools backwards or adapt to right-handed designs, forces the brain to build stronger connections between its hemispheres, creating a more flexible and integrated mind as a result of experience. These unanswered questions are not a failure of science. They are its lifeblood. They are the frontiers that are actively being explored right now. Every year, a new fossil is discovered, a new ancient genome is sequenced, and a new, more powerful brain-scanning technology is invented. The story is constantly being updated, refined, and enriched. Think of our knowledge as a small circle of light cast by a campfire in a vast, dark forest. Everything we have discussed on this journey is inside that circle of light. But the purpose of science is not just to celebrate the light, but to bravely push its boundaries, to make that circle just a little bit wider, illuminating a little more of the surrounding darkness with every new discovery. And so, we end our long journey where we began, with you, right here, in this quiet moment. The questions of the distant future and the mysteries of the deep past can now be set aside. I want you to do something very simple. Just for a moment, look at your own hands. See them as they rest in your lap or by your side. See the familiar landscape of their lines and shapes, the tools that you have used every single day of your life to navigate your world. That simple, elegant division of your body into a right and a left side, a division that you have taken for granted for your entire existence, is a living relic of our entire evolutionary saga. In your hands, you hold the direct, unbroken legacy of ancestors who first dared to stand and walk on two legs, freeing their own hands to gesture and to create. In the muscle memory of your dominant hand lies the echo of the very first Homo habilis who discovered the perfect angle to strike a stone, and in the supportive grip of your other hand lies the echo of the partner that held that stone steady. In the dexterity of your fingers, you hold the inheritance of the artists who, in the deep, torch-lit silence of a cave, reached out to leave their mark on the cold, eternal stone. And the unconscious choice you will make tomorrow morning when you reach for a cup is a silent, fleeting reenactment of a preference that was first etched into the teeth of a Neanderthal and is now coded into the very wiring of your brain. Your handedness, whether right or left, is the physical manifestation of the complex, lopsided, and miraculous brain that makes you human. It is the final personal chapter of a story that is 2 million years old. So now, as you settle deeper into your pillow, you can let these epic stories of the past gently dissolve. The great evolutionary pressures, the fierce struggles for survival, and the slow, grinding work of natural selection have all faded into the deep, quiet history that has delivered you to this moment of peace. The work is done. The frantic pace of the modern world can fall away, and the quiet, ancient rhythms of your own body can take over. Feel the gentle, unconscious rise and fall of your own breathing, a simple, sequential act conducted by the oldest parts of your brain, a rhythm that connects you to the first life that ever breathed. The images of ancient savannas and distant ancestors can now recede, replaced by the simple, safe darkness of your own quiet room. There is nothing more to analyze, nothing more to learn, and nothing more required of you now than to let go, to allow your mind to drift on the slow, outgoing tide of consciousness. The story is over, and your body, this incredible, living vessel of history, knows that its only task now is to rest, to repair, and to prepare in the profound and restorative stillness of a good night's sleep, knowing that every part of you is a miracle, millions of years in the making.